Hello. I'd like to talk about 0 to the 0 and explain why 0 to the 0 in some sense is not always equal to 1. Now, first of all, you might say, well, what are you talking about? 0 to the 0 is an undefined term. So I'm really talking about limits, of course. The other thing I want to say is that if you know what an analytic function is, then you probably are too advanced for this video here. But let's go ahead and get started. And let's go ahead and see what I mean about 0 to the 0. So the question is suppose we have f and g, two positive differentiable functions where, and what I mean by positive, I mean positive. By positive, I mean on the interval 0 to infinity on the positive reals, or including 0, where non-negative x okay, let's make that clear. Where, but not where the limit is x approaches 0 of f of x is 0, and the limit is x approaches 0. And again, I'm going to use from the right here. Now, so I want to discuss what's the limit as x approaches 0 from the right of f of x to the g of x. Now, here's the deal. If these are simple functions, for example, I don't mean simple in a technical sense, but suppose you have, let's say, f of x is something like x to the r and g of x is x to the s, where let's say r is and s are both positive exponents. Then if you try to do this, let's say x to the r to the x to the s power, it's going to be what you think it is. Let's use the log to help us out. So let's take a look at the log of x to the r, x to the s, and take a look at the limit as x approaches here. Now you're going to get what you think you should get. That's natural log of x to the r, which of course is, this is an indeterminate form because that's going to be a 0 and this is going to be a negative infinity. So of course we want to use L'Hopital's rule. And to do that, it's probably good practice to put the log up top and make this x to the minus s. Now, because s is a positive number, we get minus infinity over infinity, so L'Hopital's applies. So before we take L'Hopital's rule, let's just do something here. We have a r at log of x over x to the minus s. And by L'Hopital's rule, we take the derivative of the top and take the derivative of the bottom. So it's x to the minus s minus 1 times minus s. And that's not going to matter so much because this turns out to be the limit as x approaches 0 from the right minus r over s. And the top, let's just do a little bit of algebra. If we bring this upstairs to the numerator, we get a positive s plus a positive 1, and then we have this negative 1 right here. So we have minus r over s, x to the s, and because s is positive, that's a 0. So in fact, when we take E now, because remember we were looking at the log, so we basically take E now, and we get E to the 0 is 1, and that's what a lot of these problems, of course, boil down to. Now it's a little bit of a fact. It's a fact, and I'm not going to go into a proof here, but fact. If F and G have a valid Taylor expansion, on some open interval containing 0, we get 1 as our limit. I won't go into that because this video does not assume a prerequisite of knowing what a Taylor series is, but I put that down just in case some of you do know what it is. So for the kind of functions that you're mostly going to be used to model, 0 over 0 does in fact appear to be 1. But what if your f, your base function, is this function right here? Now you might be saying, well, wait a second, this function is not defined at 0, but notice the limit as x goes to 0 of e to the minus 1 over x squared is in fact 0. And you can see this on Desmos here, because you just try to find that, and we get y equals e to the minus 1 divided by x squared. And you can see this really, really, really flattens out near the origin. Okay? It's very, very flat. Now it turns out that the function, and technically the function is really this. So this is math, so that we have to be a little bit pedantic here. So this f has derivatives of all order at x equals 0, but does not have a Taylor series. And just as an aside, let's go ahead and just give you a brief reason why. Let's look at the difference quotient, the limit as say t goes to 0 of f of t minus f of 0 over t minus 0. So we get e to the minus 1 over t squared minus 0 divided by t. Notice what you're getting is you're getting a 0 over 0, so you can use the L'Hopital's rule calculation. But my suggestion, you don't have to do this, but I suggest, try this instead. Write that quotient like this, where you put this in the denominator, give this. It's easier to do it this way. Then a couple of things you can find that the limit in fact is 0. I won't do that here because that's not the point of this particular thing, but that in fact is that you find the derivative is 0, and if you keep on using the definition, what you're going to find is that you get 0 derivatives everywhere. But that's neither here nor there. So let's take a look at this. So we now have a 0 derivative. Now let's get back into our limits. And let's take a look now. Now by this f here, let's take a look as a limit as, let's say x approaches 0 from the right, of your f of x, where f of x is defined up here, to x to the, let's say, k power, where k is some number greater than 0, positive. Well, by definition, well, e to the minus 1 over x squared, x to the k. But we don't have to do anything too fancy here. We have e to the minus xk over x squared, just by, basic algebra. It's always nice when basic algebra is enough. And then let's expand this. This is, of course, the limit as x approaches 0 from the right of e to the minus, this is going to be x to the k minus 2. Now, this is not hard to do because let's look at the various cases. Case 1, if k is bigger than 2, then the limit is x approaches 0 from the right of e to the minus, this is going to be x to the, say, alpha, where alpha is a positive number, right? Well, this is going to be, in fact, e to the minus 0, which is, in fact, 1, what we always got here. Now, case 2 might be more trivial, but if k were actually equal to 2, well, x to the 0. Now you might say, oh, come on, that you sort of canceled this just from the get-go when you got a constant function. I know that. But let's do case 3. This is probably the most interesting thing here. Let's say k is less than 2. Then we get a limit as x approaches 0 plus e to the minus x to, let's say, the beta, where beta is now negative, right? Well, then, if beta is a negative number, the limit as x approaches 0 of x to the beta is infinity because you're dividing by 0. So this works out to be the limit as x approaches 0 from the right of e to the minus infinity, which is 0. So in this case, your 0 to the 0, in fact, gives you a 0. Okay. Now, I know this was just a basic algebra thing, but if you look at Desmos here, and let's just take a look at this. So we take this. Now let's raise all of this to, say, the to the x power. And you see what happens right there. And that's not a surprise because all that is e to the minus 1 over x, which is a homework exercise, in many calculus books. So you see right there that you see right there, I just was saving this, that in fact you can get different things. So 0 to the 0, its value does depend on how you're getting to those zeros. So, and of course, it also depends on the fact that the functions themselves are, you might say they're pathological because they don't have a Taylor series expansion. Anyway, thanks for watching.